Is there a question from the previous lecture? So today we will start with discrete time Fourier series, and we hope to even complete this in today's lecture. So we have done with discrete time Fourier transforms yesterday. So let us relook at the equations of discrete time Fourier transforms. So these are the two equations that we have seen, right? And Rohit, can you unmute yourself? Can you mute yourself? Sorry. Yeah. So these are the two equations for discrete time Fourier transforms that we have seen. And so Hn is given by this expression. Now let us consider a specific case where Hn is a periodic signal. Okay. And let us say the period of Hn is capital N. All right. So that's what we intend to do. So Hn is this, and Hn plus capital N. What should happen? This, instead of this little n, we should have n plus capital N. So this will be the expression for h of n plus capital N. Now, if Hn is periodic with capital N, what would it mean? It would mean that Hn is same as Hn plus capital N for all values of n. Okay. So first, just I have rearranged this complex exponentials into two complex exponentials, a trivial thing. And now what I'm trying to do is I'm trying to equate Hn as Hn plus capital N. So we look at these two things. What should happen if Hn is same as Hn plus capital N? Any idea?
Capital N into omega should be 2 pi m.
Exactly. So this thing should be 1, right? So from here we can say e to the power j n omega should be e to the power j 2 pi k, where k is some integer. So that this turns out to be 1. That would be the case when Hn is same as Hn plus capital N. That means what? N capital omega is same as 2 pi k. That means what? Omega is 2 pi by n times k. Okay. That means what? 2 pi by n. Let us treat it as a constant. It's a constant, right? If n is a constant, 2 pi by n is also a constant. So let me call this constant as omega naught. That means what? Omega is same as omega naught times k. What does this mean? This means that if Hn is periodic, only discrete frequencies, omega naught times k, k is an integer, omega naught is a constant. Only discrete frequencies are allowed, right? This will not be true for all values of omega, clearly. This will only be true, Hn will be same as Hn plus capital N only for discrete values of frequencies. Okay. Is this okay? I guess so. It's so simple.
Yes, sir.
Yes, sir.
I have said all of this. So now we are saying if Hn is periodic with period capital N, then this is not always true, because in this we are integrating this with all values of omega, which may not be true. This expression should only be valid for some discrete frequencies, k omega naught. So if discrete frequencies are involved in the summation, in this expression, if only discrete frequencies are involved in this expression, then I can convert this integration to summation, right? So these are the steps. So this integration will go to summation because only discrete frequencies are involved. And let me sum this over k, right? And instead of he j omega, we should have he j k omega naught. Only discrete frequencies are involved. Instead of this, I should have k omega naught. Okay. And instead of d omega, what should I have? Omega naught, because the difference between any two frequencies would be omega naught. Okay. So I will have this expression for Hn. If Hn is periodic. Okay. Now, this should be n instead of k. Should this be n or should this be k? This should be k. I was correct because I am getting Hn, so this should be k. Now what can I do more? So this 2 pi by omega naught, what is this? If n is, so omega naught by definition, how we defined it is 2 pi by n. So 2 pi by omega naught you can see is what? Is n, right? So instead of this 2 pi by omega naught, I can write as n. So I can write it like this. J n k omega naught. Okay. So does this k goes from 0 to infinity or minus infinity to plus infinity? What is the range of this k? What is the range of this k?
0 to n.
It will be 0 to n minus 1. Capital N minus 1. And why is this? Because we know omega naught is actually a phase, right? So you should only count from 0 to 2 pi. Phase goes from 0 to 2 pi. So if we include 0, then 2 pi is not included. Okay. And so in this range, because my omega naught, my discrete frequency is 2 pi by n, how many frequencies will I have between 0 to 2 pi? N frequencies, right? So my summation should go from 0 to n minus 1, including 0 and including n minus 1. So the total number of frequencies is n. Okay, so this is the expression of Hn that I will get. Maybe I will remove this thing because I also have written it so that you can see this clearly. So yeah, this is the expression that we get. And now I can replace this quantity with AKs. Okay, I can call this thing as AK because this is a function of K, right? So I can call this as AK and I can write it like this. Okay. So if Hn, remember, if Hn is periodic, then I can express Hn using AKs like this. And AKs we know is this. We have already used this definition of AKs. Any question? Now we are emphasizing the point of transform pairs. So if this expression is correct, you should also be able to find AKs from Hn, right? And what is the way by which you can do that? if we have to find AKs from HN? Tell me, what is the way by which you can find AKs from HN? Intuitively. No ideas? Okay, let us see. You can use the vector notation anyway, right? Because what is this? This is expressing Hn in terms of how many bases? N bases. We have N bases here, right? So this is the vector representation. So AK, if we have to find AK from Hn, what should we do? This is the inner product between AKs and this, right? So if we have to find AKs from Hn, what should we do? Tell me. So what is AK? It is the projection of Hn along this direction. So it should be some summation Hn, just using vector notation. What should be the values of N? Hn is periodic. So this should be this, right? Clear? Divided by energy of these things. Whatever that energy might be. What is the energy of these things? Energy of bases. What is the energy of this complex exponential?
So one for each thing. So will that be, I guess, N?
Exactly. How do you find the energy of this? So this, you have to compute this from, this is the energy, and this you can see as simply N, right? So even without doing any fuss, just by using the vector notation, we can easily compute AKs from Hn, right? So AK would be this. Is this idea clear? So Hn, see what we are doing. I think I have talked about vectors too much. So this should be clear by now. So here I am writing out a vector in terms of the projection of that vector along a basis. Okay, so if I have to find the component, which is AK, of this vector Hn along this basis, this could be obtained by taking the inner product of Hn with this basis, and this is the expression for the inner product, right? Because Hn is periodic, I only need to consider one period, and then I divide this with the energy of this basis in a period. Energy of this basis in a period is N. Use this expression. So we can simply get AKs.
Sir,
Yeah.
sir, could you explain how did we get that minus JK in the numerator?
Because this is the inner product, right, of Hn and this. I have to find inner product of Hn where this inner
Yes.
product of Hn with this has a conjugate here, right? So we get a
Yes.
minus. Any other question? Okay. In the slides, I have done this in a different way, which I will not talk. If this is clear, I think that's it. So I will skip all of this because it's complicated. Finally, you will get these two expressions. Deriving this from the vectors idea is very simple. Okay, so these are the two equations that we can use for discrete time Fourier series. You can look for an alternative approach if you do not want to make any assumption on this vector analysis and so on and so forth, you can look at the slides and see for yourself. So these are the two equations that we will use for discrete time Fourier series. Clear? Okay. So now you have to look at these two statements and tell me how many of them are correct statements. Are these AKs, the first statement that I'm saying is, are these AKs periodic with period n? So we have said the signal is periodic with period capital N. Are these AKs also periodic with period n? And then the second statement, which we have already seen, is there are only n orthogonal vectors required to express a periodic discrete time signal, which is correct. We have already seen this. Why? Because between 0 to 2 pi, if the difference between two vectors frequency is omega naught, then you will have n orthogonal vectors. You can also prove, I have not proven this, that e to the power j k omega naught n is a k1 is periodic with e to the power j k2 omega naught n. Prove this, that these two bases are periodic if k1 is different from, these two bases are orthogonal if k1 is different from k2. Prove it. Assume k1 and k2 to be integers, different integers. Prove that the inner product between these two signals in a period is 0. Okay, you can do this exercise. So we have already seen that this is true. Let us look at this statement. So let us look at this. So if we consider AK plus N, what would happen? Instead of K, we will have K plus N. And again, we can decompose this single complex exponential into two complex exponentials. Right? And you see that this is going to be 1 because we have n omega naught n. So this is simply 2 pi n. 2 pi n, if n is an integer, is 1. Right? So this can be ignored. So if we ignore this, we simply get AKs. So AK plus N is same as AK. So what am I saying? If my signal is periodic with capital N, if Xn or Hn is periodic with capital N, then the coefficients are also periodic with capital N. That's good. Okay. If you have any doubt, please stop me. Okay, fine. So we have seen this. And we have also seen that between 0 to 2 pi, there are n complex exponentials. I will not repeat it. So what does this mean is, if you have a signal which is periodic with period 3, okay, the signal is periodic with period 3. How many complex exponentials we will have? 3 complex exponentials. If the signal is periodic with period 4, how many complex exponentials we will have? 4 complex exponentials. Okay.
Sir, I had a doubt.
Yeah.
So, if AK is periodic with n, but like in the summation, you wrote Hn equals to 0 to n minus 1 AK. So doesn't that imply that AK for any n that any k that is not 0, that is not between 0 and n minus 1 will be 0?
Sorry, which expression you are talking about?
So Hn equals to k from 0 to n minus 1, AK
This one.
to the power. Yeah,
This
so
one.
doesn't this imply that any AK for k not between 0 and n minus 1 will be 0?
AK for K between where to where?
For k not in between 0 and n minus 1.
No, it doesn't imply. See, what we are saying. So if now you suppose if you know now AKs are periodic, okay, with period n. So you can see that this entire signal, this entire thing is periodic with period capital N, right? This entire thing. When we have a periodic signal which has got a period capital N, you should only be considering summation in that single period. Why is this? Because if you would have considered summation k going from minus infinity to plus infinity, then of course this summation will become infinite, right? Or there is a very high probability that this summation will become infinity, right? Or its energy of xn will become infinity for sure. If you are having a periodic signal, that is any periodic signal. If you are having a periodic signal, let's say like this, let it be continuous time or discrete time, doesn't matter. What is the energy of this periodic signal? Energy of the periodic signal from between minus infinity to plus infinity is always infinity, right? Its energy is infinity. What is the energy of e to the power jk omega naught n? From minus infinity to plus infinity, it is also infinity. Now, if we would have used this summation going from minus infinity to plus infinity, you would definitely run into trouble dividing this by infinity, because then the energy of this basis would be infinity in that minus infinity to plus infinity range. And there is no extra information you see you will get by considering other than one period, because the signal is repetitive. If it is repetitive after a certain time, then there is no extra information in here or here or here, wherever. Thus, whenever periodic signals are involved, it is safe and it is in our best interest to consider this periodic signal only in one period. Okay, it's a common practice, and divide by the energy of basis in that one period. Now let us say if you are unhappy, okay, and you say no, I do not want to do this. I want to consider the signal in 10 periods. You can do that. If I consider the signal in 10 periods, let's say 0 to 10 n minus 1. You can do that. But then the basis, this energy of this should also be calculated in 10 periods, right? So whatever you will get, it would be divided by the energy of basis in that period, and you will have the equivalent expression. There, nothing would change. Thus, as a common idea, as a common practice, it is only important that you consider a signal. If it is a periodic signal, you consider the xn in one period and you find the coefficients also in that one period. That doesn't mean that outside this period everything is zero. It doesn't mean that. Okay.
Yes, sir.
Any other question? Now there is one very beautiful thing that is happening here. Yeah, I might be incorrect here, so it's fine. There is very beautiful thing that you can see here. What is that beautiful thing? Beautiful thing is, let us look at xn again. Xn is periodic, okay, and discrete. Fine. So let me draw some particular xn. Let us think it like this. Periodic, what does it mean? It means that the information outside a period is repetitive, so there is no information. All of this is jargon. So all information about Xn is contained only in one period. So this is what this one period conveys everything about Xn. And how many samples do you have in one period? You have, in this case, you have 3 samples. That means you can, if you can communicate these 3 samples to someone, you are transmitting the complete information about Xn. And as an engineer, as someone who thinks that science is consistent, you should see that when you take its Fourier transform also, you get some AKs. So how many AKs do you need to transmit to communicate in entirety about Xn? The three samples. It's very consistent, right? It's a transform equation. That means you are not creating extra information. You are not losing out on information. Your information content remains intact, right? When we are looking at these transform pairs. That means you are not creating information. You are not losing out on information. So if you could communicate everything about Xn using 3 samples, it is but obvious that you would communicate everything about its Fourier transforms also by using the 3 samples. So look at this beauty. So if you have a periodic signal and a discrete signal, you should imagine that its Fourier transform should also be periodic and discrete. Okay, isn't it? Do you agree with this idea? Have you got it?
Yes, sir.
Yes, sir.
Now let me just go back. Let us look at other equations also, other transform equations. Xt. Xt, which is continuous. And what? Let me assume it to be aperiodic. This type of signal will have minimum information because it's periodic, right? And it's discrete. So minimum information only in one period, and even in that period, the samples are discrete. So no problem. Look at this, contrast this with this. Continuous is very problematic thing, right? When I'm saying continuous, I mean continuous time. So that means this signal has information at all continuum values of times. So it's disastrous. It's also aperiodic. It's also disaster because you do not know how far you have to consider the signal. Okay. So when we do its Fourier transform should also preserve these two properties. Its x omega should also be continuous and should also be aperiodic. Right? We have already seen this. I'm just motivating these things in a different perspective. Isn't it? So x omega is also continuous in frequency and aperiodic. Right? Now let us look at the third case. When this is continuous and now when this is periodic. Periodic is better than aperiodic, right? From information point of view. Because when I'm saying my signal is periodic, I say that after a certain time, we do not have to consider the signal at all. When I'm saying the signal is aperiodic, I do not specify exactly to you when should you stop considering that signal. So if my xt is continuous and periodic, continuous is bad, this is bad, and periodic is good. Okay. So what is the nature of its Fourier transform? You already now know this, right? We have proven it. I'm just motivating you, giving you some slight picture of this from information theoretic point of view. It's Fourier transform. What is it? It's Fourier transform, if you see, is aperiodic and discrete. So this is bad and this is good. So you see that because my xt has one good characteristic, its Fourier transform also has one good characteristic. Okay, similarly, if my xt is what? Which case is remaining? I think discrete and aperiodic. Is this remaining? Yeah. It's Fourier transform, if you see. How is the Fourier transform? Periodic and continuous. So you see the signal has got one good characteristic from information point of view. This Fourier transform also has got one good characteristic from information point of view. xt, this one has got this as a good characteristic. This is bad. So its Fourier transform also has got one good characteristic. Okay. Fine. This is bad. If the signal has got both good characteristics, its Fourier transform will also have both good characteristics. If signal has got both bad characteristics, its Fourier transform will have both bad characteristics. So some insight into these transform equations. Is this okay? Clear? Okay, thanks. Let us, we have seen this. We have seen this. Yes. Now come back to discrete time Fourier series. I will talk about the relationships between these Fourier transform pairs also after some time. Now I want again to focus back on this discrete time Fourier series. So looking at these two equations, no convergence issues, right? This is a finite sum, right? So it cannot become infinity. This is also finite sum. It cannot become infinity, right? So there are no convergence issues. Actually, we are dealing with only finite number of equations. Okay, the finite number of equations in this, right? And there are finite number of unknowns. So there are no convergence issues. That is one thing. Why there is no convergence issue? Because finite summation is there, right? So everything has to converge to a certain point. Second point is there is a strong duality in discrete time Fourier series. What do I mean by this? We have seen that there was a duality in where in CTFT there was duality. Continuous time Fourier transform, there was duality. Why? Because xt was what? It was aperiodic and continuous. X omega aperiodic and continuous. So the nature of signals xt and x omegas are same. Both these signals were bad. They have the bad characteristic from information theoretic point of view. So xt and x omega should have the same form. And so there is a strong duality between these two transform pairs. Now in discrete time Fourier series also there should be a strong duality because both these signals xn and ak's, they have good characteristics. Both characteristics are good. Discrete and periodic. What better can you ask? AK is also discrete and periodic. Right, so there also has to be a strong duality in DTFS. Right, this is a motivation. It's not a proof. Okay, proof you can look up at in the books, or we will talk little bit more about duality. But I'm just motivating. Why should there be a duality? But there was no duality where in DTFT there was no duality. between DTFT pairs. Why? Because the signal and transform characteristics were different. XT was what? XT was discrete, aperiodic, but its transform was periodic and continuous. So the characteristics were different. So there was no duality in DTFT, but there was a duality between DTFT and CTFS. We have seen this. A very strong duality. Okay. So again, in DTFS, there should also be a strong duality because the nature of the signal and the transform both are having the same shape, same form. Okay. Okay, now let us do some maths. What is the DTFS, discrete time Fourier series, for this signal? So let us assume that this is periodic with capital N. What is this signal? We have already seen such a signal, right, in DTFT case.
Sigma m del n minus mk.
Yeah, so I will not do this in detail. I'm just trying to motivate you. So if you look at A case, you can of course use this expression, change the limit from minus n1 to plus n1, have 1 instead of xn in this period, and at remaining places you can make it 0 and you can work out the maths yourself and you will get this form of expression. Right. We also got this form of expression in DTFT where we did the maths in detail. The only difference, what, instead of omega naught, instead of k omega naught, it was simply omega, right? That was the difference. So here, because my frequencies, all continuous frequencies are not allowed, so instead of omega, we should have k omega naught. That's obvious, right? So that's the only difference. Important point to note is, and I think I will talk more about this thing when we do sampling. In continuous time signals, sin x by x or sinc x, it's a very important signal and it plays a lot of roles, especially in sampling and interpolation. We will see this. We haven't seen it yet, but this sinc x plays a very important role in CT case. The same role in DT case is played by this sin nx by sin x, the same role. And there is a reason for it. In CT, if you take a rectangle pulse, it has got a Fourier transform which is sinc. In DT, if you take a rectangular signal, then its Fourier transform is of this form, sin nx by sin x. So important point, you can note it down and we will use this fact later. Okay, so the only example, then there are certain properties of DTFS which you should know. First one is duality. You can look at the proof in textbook. I will not repeat the proof because we have done all these proofs in a lot of details for other cases, other domains. So there is the duality in DTFS. Parseval's theorem is also valid. What does Parseval's theorem says? Inner product in time domain can be computed by taking the inner product in frequency domain. That's it. Again, this is valid. Finite difference is also valid, right? So we have also seen this property. It's also valid. Okay, you have to check. I think this is wrong. It has to be omega naught. Check this out. Okay. And then you have a running sum. This is also valid, same as it is. However, for running sum, same as in the case of CTFS, This A naught should be 0. Otherwise, this signal will not be periodic. Right? Because we are talking about the periodic signals. If the mean of xn is not 0, then if you integrate that signal, this will not remain a periodic signal. It has to be a periodic signal. So by definition, xn should have got a 0 mean if this signal has to be periodic. So we can use this relationship straight away. We have seen that we had certain problems in using this relation straight away in case of DTFT if the signal mean is not 0. But here by definition, if this has to be periodic, the signal mean has to be 0. So you can actually inverse this to get this expression. Fine. So certain properties which you should go through the textbook and see it for yourself.
Sir, why signal mean 0 if the signal is periodic?
We have seen this, right? If you take a signal like this, it's easier to draw CT signals. That's why I'm drawing this. If suppose you have a periodic signal like this, if you integrate this periodic signal, this will
Okay,
go.
for it to be stable.
Yeah, this will be like this. It's not a periodic signal.
Yeah, okay.
Okay, so look at these properties now. Let us do something different for DTFS. So when I look at this expression, what do you think? It simply means that we can use matrix to solve this expression, right? Because everything is finite on both sides. Xn is finite, AKs are finite. So I can use matrix. So if I have to compute x of 0, so let us look at x of 0. So this was summation AK e to the power j k omega naught n. N is 0. Right? So that means this is A0 plus A1 plus A2 plus A3. This is what x of 0 is. So this is 1. If you look at this thing, this is 1, 1, 1, 1. Because of this 0 sitting, this will be 1. Then we simply have to multiply this with A0, A1, A2, A3. And you can compute the value of x of 0. Suppose we have to find x of 1. Then this has to be 1. Okay, and then this is A0 plus A1 e to the power j omega naught plus A2 e to the power 2j omega naught plus A3 e to the power 3j omega naught. Okay, so x of 1 is A naught times 1 plus A1 times e to the power j omega naught. 2 by n is omega naught. A2 times e to the power 2j omega naught, and so on and so forth. Idea is there is a matrix relationship between xn and AKs. Clear? So you can use, because we know matrix also quite well, so you can use matrix representation to use this. So if you look at this matrix, there are 4 equations and there are 4 unknowns, right? So it's very simple to solve all of this using matrix. Now let us go a little bit deep. I can substitute the values of complex exponentials, which in this particular case came out to be like this. So I can compute x0, x1, x2, x3 in terms of A0, A1, A2, A3. Now if I have to find A0, A1, A2, A3 from x0, x1, x2, x3, can we do this? Yes, right? You know inverses in a matrix. So this is a square matrix, its inverse exists. You can check its determinant will not be 0. Okay, so if we compute the inverses which exist in this case, we can compute these A0, A1, A2, A3 also in terms of X0, X1, X2, X3. Straightforward. No problem. Fine. But now if you look at these two things, we will see one problem that may appear. And that problem is the number of operations. If just I focus on multiplication, how many multiplications do you think you have to do in this to get these values of X0, X1, X2, X3? How many multiplications in this case?
16.
16. Number of multiplications is 16, right? Because you have to multiply 1 with A0, this with this, this with this, this with this, and you have to do 4 multiplication 4 times because there are 4 rows. So total number of multiplications are 16. And you can show in general if we are looking at Xn, which is periodic with capital N. So number of multiplications will increase as or grow as n square, which is bad, which is not the most efficient thing to do. Okay, so this is one problem in this DTFS, discrete time Fourier series. Okay, so now I am trying to look at a way by which I can reduce these number of operations. Okay, is the motivation clear? Because I have proven that if I conventionally use this DTFS, it's going to be bad thing, right? So many operations. So let us see a way by which I can reduce the number of operations. And the idea is use what is known as fast Fourier transform, FFT. Some very bizarre nomenclature and notation and naming by electrical engineers. Actually, this DTFS, discrete time Fourier series, to confuse everyone around on this earth, engineers have started calling this DTFS as DFT. DFT stands for discrete Fourier transform. Discrete Fourier transform. So DTFS and DFT are one and the same thing. DFT is same as DTFS, no difference. Okay, DFT, if you think just DFT looks closer to DTFT, right? But it has nothing to do with DTFT. DFT is same as DTFS, so engineers started calling DTFS as DFT, discrete Fourier transform. Just bad naming, I would say. And then there is an algorithm, many algorithms in fact, which have been proposed to calculate these DFT in a faster way. That means by using less number of operations. These algorithms are known as fast Fourier transform. So what is fast Fourier transform? Fast Fourier transform is a way by which you can compute DFT by using less number of steps. And what is DFT? DFT is nothing but it is DTFS. Okay. So now let us look at this one particular algorithm of FFT which was proposed first, right? And then there are various other improvements to this FFT algorithm. So what does this say? Let us look at this strategy and then we will eventually understand this. It says that if you are having a signal Xn, just motivation of length 2n, let us say. Okay. Instead of calculating DFT of Xn with length 2n, let us compute DFT of Xn of length n. And from these things, we will try to interpret what would be this. So you have a big signal of length n. Instead of thinking about this at one go, let us break this down into signals of half of length and let us try to compute its DFT, and there might be some advantages in doing that. And this approach is known as divide and conquer.
Here
We
2n
will-
is the period, right?
2n is the period, yes.
Okay.
Okay, so I will talk about what this 2n is maybe tomorrow, but for the moment you can believe that 2n is the period. So I have few minutes left, so let me try to complete as much as I could. So instead of using the previous matrix, let me change my notation slightly. It's just a notational difference. So I am defining this thing as W4. Okay. Why? Because it's just a function of what is this quantity. And this quantity is 4. So let me call this as W4. Then I can write these various complex exponentials like this. W4 to the power 0. Okay, so this will give us 1 or 1 by 4, because if you look at this, you had 1 by 4 here. Okay. And if I look at this, then we can get to various complex exponentials. Fine. So remember that this 0 what would be its function of? This 0, this 1, this 2, and this 3. What it would be function of? So there are two things playing in, right? So if you look at that summation, this complex exponential e to the power j omega naught kn. Omega naught in this case is 2 pi by 4. So that is done. Okay. The kn, what is the k and what is the n? That will decide the power of W4. Okay. So in this case, because this is 0, so I have to compute this thing. So in this case, if I look at this, so k is 0, right? So these are AKs. So k is 0 for this. So of course, the kn is also 0, and I get 0, 0, 0, 0. Done. Here k is 1. If k is 1, then I get simple n. So this 0 multiplied by this 1 multiplied by this 2 multiplied by here, this 3 multiplied by this. Okay. Here my k is 2. So let me look at kn. So 2 times 0, which is 0. 2 times 1, which is 2. 2 times 2, which is 4. Right? But 4, again, you have the phase wrapping or frequency wrapping. So 4 is same as 0. Okay. Now 2 times 3, which is 6. But we have to consider this modulo 4. So 6 modulo 4 is 2. Right? You understood, right? This modulo thing that I'm talking. Because there is a frequency wrapping. So let me just illustrate this if you haven't understood. So if this is e to the power j, forget about minus 2 pi by 4. And suppose I have 6. Okay. So what is this? This is 12 pi by 4. Right? 12 pi by 4. What is this? This is also, if I write this as 2 pi. 2 pi plus what it would be? 2 pi by 4 times 2. Isn't this?
Yes, sir.
So we are writing everything modulo 2 pi. Modulo 2 pi here means modulo 4. Okay, so this thing is same as this thing. So that's why I have 2. Similarly, Kn 0 will mean 0. K is 3. So 3 times 1 is 3. 3 times 2 is 6, which is 4, modulo 4. 3 times 3 is 9, modulo 4 is 1. Okay. So let us start talking about these things in the next lecture. I will start from this point in the next lecture. Okay, any confusion on this part so far?
Sir, here does this notation refer to W4 raised to power this thing?
Yeah, it's W4 raised to power.
Sir, if that is the case, then when W4 raised to power 0, then even the 1 by 4 factor will be like omitted.
No. So let me define this notation. I should have defined this. So W4 raised to power m, if this is m, it means that 1 by 4 we do not change. This is e to the power minus j 2 pi by 4 times m. This is the meaning. Okay.
Yeah, fine, sir.
Okay. Thank you so much. Thanks for your time. See you tomorrow. Not tomorrow, Friday.
Excuse me,
Bye
sir.
bye. Yeah.
So I have a very poor doubt. I mean, actually, I'm confused between this Fourier transform and Fourier series. Like at this point of time, I should not be. But the thing is, after so many transforms and series, how do we differentiate them? The series and the transform. The basic difference.
Yeah. So this is a very good question and a natural question. Because we are doing so many transforms, it's but obvious that you will get confused, and that's why we will have lecture on Friday which will tie these 4 transforms together, and you will begin to see these 4 different transforms as one transform.
Oh, okay. Yeah.
So you have to wait for lecture on Friday. There I will solve this doubt, right?
Yes.
Thanks. Lecture on Friday is very important. It is the basis of this course. So I request all of you to attend this. Okay, bye. Take care.